Hi folks, it's Mr. Moodledge here with another video. This time we're taking a look at a two-part lesson on transformations and reflections. Okay, so for the first part of this video, or for the first part of this lesson, the focus is going to be on looking at transformations and mapping rules. And then the next part, or the next lesson, is going to be graphing functions with transformations applied to them. Okay, so just to begin, we're going to look at the key 7 parent functions that we are going to look at extensively in MCR3U. There are others like trig functions as well, but these are the main ones that we begin with, okay? So there's the linear function, f of x is equal to x. There is the quadratic function, f of x is equal to x squared. This is review from the last video as well, so you can go check that out. Lesson number 3, parent functions, if you haven't already. But we have the square root function, f of x is equal to root x. There is the cubic function, f of x is equal to x cubed. This one's really interesting, the exponential function, f of x is equal to 2 to the power of x, because it is one of the functions that has an asymptote. As we can see here, as x gets smaller and smaller and smaller, y also gets smaller and smaller, but it never crosses the y equals 0 line, which we call an asymptote. Another interesting point here is that traditionally, when we are graphing these for the very first time, we will make a table of values, as we can see here, with many more input values and then calculate the output value. But when we're doing this, after a while, we only need to consider a handful, like a few points. So for example, these are like benchmark points, like 0, 1, -1, like the input values. And then it's easy to calculate the output values for those. And then we can include one more if we really want. So we're looking at around 3 to 5 points maximum. Okay, so we can get the general shape of the curve of the function. Here we have the absolute value function, which is the shape of a letter V. And lastly, we have the reciprocal function right here, which has these two pieces, and it has two asymptotes, one at y equals 0 and the other at x equals 0. Okay, so that's just a review of last video. Now, what's new for this video is we're going to look at transformations that occur to these parent functions and describing them. So if we have an equation that's like y equals 2x cubed plus 5, I want you to think about what is happening, what is directly, like if you think of it in terms of like brackets, like this, for example, or like just the input, it's helpful to think of everything that's happening outside the input, and we'll see this when we write it in function notation even clearer, is going to affect our y. So essentially this 2 and this 5 are going to affect our y, whereas stuff happening inside, right now it's just x here on its own, so there are no horizontal things affecting that, would affect it horizontally. Whereas here, it's x plus 5, and these are the absolute value bars, but this is treated like the new input there. So we could see here that would affect us horizontally, okay? All right, I want to make a little bit of like a legend here, just to make our lives easier. V is going to stand for vertical, H for horizontal, S is a stretch, C is a compression, T is a translation. Sometimes we call that a shift as well, but I don't want to double up on stretch and shift because they both have the letter S, so I'm going to stick with translation T. And then by a factor of, we use this when we're dealing with stretches and compressions, we can just shorten that to BAFO, B-A-F-O. Okay, so for example here, if I'm looking at this equation right here and I want to describe what are the transformations happening to the parent function, which is y equals x cubed, or f of x is equal to x cubed here, what is happening to that parent function to get this? So describing the transformations. This 2 is a vertical stretch because it's that 2 is greater than 1. It's a vertical stretch by a factor of 2. So with vertical elements, it directly behaves just like we expect it to. We multiply, by 2, and we shift up by 2, As we could see here, this is a vertical translation up 5. Okay. Moving on to the next one right here. When we have a negative a value, so that there's two parts to this. The negative, first of all, we have to realize that this is affecting us vertically. Same with this 4, and this is affecting us horizontally. So this negative means that we are going to have a vertical reflection. In other words, we are reflecting about the x-axis. So we are reflecting if this is like this, our reflection would be an upside down V now, okay, after we reflect. And the 1/3 here means that we are compressing vertically. So we have a vertical compression because it's a number between 0 and 1. Whenever it's a fraction like this, a number between 0 and 1, we're going to get a compression. So we have a vertical compression by a factor of 1/3. And we say 1/3 here because every y value that I input into this equation is going to get multiplied by 1/3. So that's what a compression is, right? And then it'll move up via a vertical translation 4 units up, right? So that's the vertically, that's what's the transformations applied to my new function here from the parent function, which was just f of x is equal to the absolute value of x. And lastly, don't forget we have in the x direction, my transformation is a horizontal translation, 5 units to the left. So what that means is that with the x, just as we expect, whenever there is a sign here, which is positive 5, we do the opposite of that. So it's going to be negative. It's going to move to the left. Actually, it's x's are weird. They behave opposite to how we logically want them to. Okay, that's good. Okay, next here we have a point given on a parent function, y equals x squared. And I want to figure out where will that point, which is actually on this parent function, where would that point map to after applying these transformations, right? So it's not the same thing as just taking this point. It's not asking me find the value of y or the output when x is equal to 3, right? This is a brand new function within the same family. It's a transformed function. But I want to find explicitly what happens, how does this point get mapped under those transformations? So this is where mapping rules apply. Okay, here I want to go ahead and establish one at a time what each transformation does. So the 1/3 affects me vertically because it's outside the brackets, right? It's outside this input right here, so it's going to affect me vertically. So what I do is I have a point here, 3, 9. If I write that, 3, 9, if it affects me vertically and it's a compression by a factor of 1/3, then that means I'm going to multiply that y value by 1/3, or in other words, divide it by 3, and I get the new point 3, 3 after I've applied that compression. Next, I can go ahead, I don't have any other stretches or compressions, so I'm going to go ahead and look at my horizontal translation here. So it means it's going to translate 5 units to the right. So that means my x value, which was originally a 3, now becomes 8 because it's plus 5. Okay, the y value stayed the same after that horizontal translation. However, don't forget there is a vertical translation here. -7 means 7 units down. So I have to go down from 3 here and I get to -4. So my new point is going to be 8, -4. And this point is going to be on this transformed function. It was literally the 3, 9 got transformed into 8, -4 under these transformations, right? These transformations that we have here, those 3 right there. I could generalize this because you can imagine how tedious this would be for if I wanted to draw the entire graph, right? This is why I can generalize it for any x and y using my x and y coordinates, right? Points as x and y, so as a variable. So x, really every x value, the only thing affecting my x here in this case is a horizontal translation, so it's going to I'm going to add 5. Vertically, I have a stretch of, sorry, not a stretch, I have a compression of 1/3. So I'm going to multiply that y value by a factor of 1/3. And then I'm going to subtract 7 because I have a shift translation 7 units down, right? So minus 7. So now if I wanted to really check this with what I got, I'd plug in 3 into my x here. Let's change that color. And then I'd plug in 9 into y, and I'd simplify this and get 8 negative 4, which is what I expect. So a little side note here, this will play especially when we are graphing as well. So a little bit more on this next lesson, but just as a little bit of a preview, you always want to do reflections, stretches, and compressions first, and then translations. You can see here clearly it's bed mass as well. But also, if you don't do this, if you think of it like practically, if you move something, so if you translate something and then stretch it, you're going to distort the actual graph. So you want to translate it, stretch it, reflect it, and then move it. That'll give you the proper picture. Okay. The last question here for this lesson is we have a point now, which is like 3, 4, and it's on a function. I'm not given what the function rule is. That's okay. The function, for all I care, for all intents and purposes, could be like, some random squiggle like that. Let's just say on that squiggle, there is this point 3, 4. 3, 4 is contained in that squiggle. Now I'm trying to figure out what happens to that point under these transformations. So I'm not actually asking what is the function here. I'm just asking how does that point get transformed? So that again is how I'm going to make use of my mapping rules. I'm going to look at, okay, it's easy to see here now when it's written in function notation like this, that this is the stuff affecting me. Everything inside my input here is going to affect myself horizontally. Everything outside the brackets and outside the f of x minus 7 here is going to affect me vertically. So I'd say my x, the only thing affecting me is that shift of translation of 7. So it's going to be x plus 7. And my y is going to get stretched by a factor of 2, so 2y, and then translated 5 up, so 2y plus 5. So if I had the point 3, 4, this would be, my x would be 3, so 3 plus 7 is how I get 10. And then my y would be 4, so 2 times 4 is 8, plus 5 is 13. Okay, here's another example here. If I had y is equal to negative 1 over 4f, bracket, negative x plus 8, close bracket, function of negative x plus 8, and then close bracket, right, plus 6, then here's a little important thing that I want you to know for here. This is also something that'll play on, especially in a future lesson, when we introduce horizontal stretches and compressions, is that you always want to factor out the coefficient of x. So always factor out the coefficient of x inside the bracket. Okay, so what that means here is that here we have a negative x plus 8. I don't want a negative x. I need to make that a positive x. So I'm going to factor out a negative. So I put a negative here, put brackets, and then literally the signs change, right? So it's going to be x minus 8 inside the bracket. Good. So this is what I get when I factor. And it's necessary to do this because this is actually going to give me the proper translation horizontally, whereas this is going to give me the reflection. Okay. So now if I take a look here, I could go ahead and describe these transformations, right? Again, the things inside the brackets affect me horizontally, the things outside vertically. So, sorry, just had to take a sip of water. So if I just look here at my x and y, I'm going to map them using the transformations. My x becomes, the only thing affecting my x is this reflection right here. So this is a horizontal reflection. So I'm going to multiply it by negative x right here. and then it's going to shift 8 units to the right. So as we can see right here. Secondly, when I take a look at my y, I'm going to have a vertical reflection or a reflection among the about the x-axis, and it's going to be compressed vertically by a factor of a quarter. So I just multiply the y-coordinate by negative a quarter, and I add 6 because there's a translation 6 units up. Applying these to the point 3, 4, I'm going to get negative 3 plus 8, which is 5, and then 4 here. Negative 1 over 4 times 4 is negative 1, plus 6 is equal to 5. So under those transformations, this is the new point that gets transformed. 3, 4 becomes 5, 5 under this function transformation. Okay, very good. So that is all that I wanted to say for this lesson. You can now go ahead and do these questions from the Nelson 11 functions textbook. Good luck and have a great day. Thank you.